Alright guys, tonight we're going to talk about something called chemical equilibrium. This is the last part of our Unit 7 chemical reactions that we're going to be studying. Okay, so the first thing we need to understand in order for us to understand chemical equilibrium is the fact that some reactions are what we call reversible. So far in our study of chemical reactions, we've looked at reactions that are irreversible, meaning the reactants turn into the products and that's it. Well, here we see that we have what we call a dual arrow. So really what it looks like is like this and like that. I don't have the capability of typing that. We call this a dual arrow here, okay, because it goes in two different directions. This reaction here of the decomposition of carbonic acid is what we call reversible. Carbonic acid will decompose into carbon dioxide and water. However, water and carbon dioxide can combine themselves to produce carbonic acid. So the reaction can go forwards and backwards, or forward and reverse. Now you might be wondering, where does a chemical reaction like this occur in our universe? This is something that occurs in our bloodstream with carbon dioxide. If we have too much carbon dioxide in our body, we become acidic because then we have a buildup of carbonic acid. This also is a reversible reaction that occurs in soda. We pump carbon dioxide into our soda to carbonate it. However, that carbon dioxide will react with the water in soda and form carbonic acid. But then the carbonic acid decomposes into carbon dioxide and water again, and that's how we have our fizziness. So what is exactly equilibrium? Chemical equilibrium is the state in which both our reactants and products in a given reaction are present in concentrations that have no further tendency to change with time. So for as many reactants are turning into products, there are a certain number of products turning into reactants. They're both being formed at the same time. And when a reaction is said to be in equilibrium, the rates of the forward and reverse reactions are equal. This is extremely important here. The rate at which the products are produced and the rate at which the reactants are produced is the same. The amounts are not necessarily the same because the concentrations can be different, but the rate of production is the same. There is no overall change in the concentration of our reactants or products in a particular reaction. And when this occurs, we call this dynamic equilibrium. Things are changing, but the concentration is not. So it appears that there is no actual reaction taking place. So here we can take a look at our carbonic acid decomposition reaction again. And the rate at which the carbonic acid breaks up into carbon dioxide and water is the same as the rate at which the carbon dioxide and water are combining to form the carbonic acid. So this happens in equilibrium. Now there's a principle that goes along with equilibrium, and I've heard two different pronunciations of his name. I've heard it as Le Chatelier and Le Chatelier. Either way, this is his principle. And the principle gives us an idea of the behavior of an equilibrium system when changes occur to the system. So basically, what happens to a reaction when we put some stress on it? What would be some stressors? We could change the amount of the reactants or the products, meaning their concentrations. If we add more carbonic acid, does more carbon dioxide and water get produced? Or if we're in the presence of more water, do we make more carbonic acid and go reverse? Pressure and temperature are often components to a chemical reaction. Say a chemical reaction does not actually occur unless you hit a certain temperature or unless a certain pressure is achieved. If we reduce the temperature or increase the temperature, does that affect the system? And Le Chatelier says that it does. And we can force a reaction to shift from equilibrium to a new equilibrium in which the concentrations are different. The amount of catalyst, if a catalyst is present, can also be changed and considered a stressor to a reaction. A catalyst is what makes a reaction move forward, having the reactants produce the products. So if we increase the amount of a catalyst, presumably the rate at which the reaction moves forward will be shifted. And so everything shifts to accommodate that. If we take away the catalyst, that slows down the reaction, and so that allows the products to recombine to form the reactants again. And then the system would shift to the left or in the reverse direction. So how exactly does all of this work? Well, here's an application to Le Chatelier's principle. I've got some pictures here of some slides from a FET. So here I have added 3A particles and I initially added 5 A's and 5 B's, BC compounds in this single displacement reaction. We've got A plus BC yields AB plus C, but then it's reversible. So initially I started out with 5 A's and 5 BC's, 5 of each. But as the reaction has taken place at a fairly decent temperature, kind of low, and a good amount of energy here, sorry about that, we can see that we're in an equilibrium where we have 3 of each of our reactants to 2 of the products. And so this is going back and forth. But what happens if we put some stress on this system? Well, let's take a look. Here I've added more BC reactant. So the concentration has changed. And look at what's happened. I've shifted the reaction more to the product side by increasing this. You can look here on the bar graph. I definitely have an increase in my BC, but I've raised my products up and I've lowered my reactant A down. So when we add more reactants to a system, we shift the reaction more toward the products and we produce more product. What happens if I change the temperature of the system? Well, temperature is considered a stressor as well. So here you can see that I've increased temperature. So my total average energy has gone up. I've also forced this more toward the product side. You have to be very careful in reading problems, because if something needs to happen at colder temperatures, you will not have the same result. However, here, because of the higher temperatures, the particles move faster. When they move faster, they have a higher tendency to interact and collide, which then shifts our products again. So the original box, we had 2 of each of the products, and now we've got 3, simply because we increased the temperature. That's it for tonight. This is your introduction to equilibrium and Le Chatelier's principle. We'll talk more about this in class, and please make sure you have your book tomorrow. We're going to work on some book problems. Have a great evening.